Okay, hello everybody. Welcome to the SETI Institute Lunchtime Colloquium Series. Normally we have a visiting scientist present their research, but today we're going to have our scientists in training, our REU students, present their research projects. So my name is Doug Caldwell. I'm the director of the REU program after having taken over this summer, finishing out for Jean Shar, who's been the director for the past 3 years now. And this is the 11th year that the SETI Institute has run this REU program for summer interns. And so for today's colloquium, we're going to have the students have prepared a 3-minute, 3-slide talk. So it's going to go kind of fast. And we're going to hold them to 3 minutes. I have a bell, but I promise not to use it if they're not spending too much time over. But we're going to have some short talks. We'll change out the students, and the slides are all up here. So if you're the next student, and the time's running up, get ready, start coming up here so we can get through these. And then we're going to have questions at the end. So we'll have all the students available to come up here, and you can ask questions about any of the talks that you'd like. So my official 3-minute time starts now. If someone wants to time me, I can. My name is Doug Caldwell, as I mentioned. I'm an astrophysicist here at the SETI Institute. Our research experience for undergraduates program, REU program, is funded by the National Science Foundation with some funding from the NASA Astrobiology Institute and some support from the SETI Institute. This summer we have 11 students who are selected to work with SETI Institute researchers for a 10-week research program. It's been very fast and very packed full of things to do. Their research falls under the umbrella of astrobiology, and it includes topics in astrophysics, planetary science, exoplanet studies, and earth science. The students have carried out their projects at the SETI Institute and at NASA Ames, and they've taken part in NASA mission design studies, carried out lab experiments, analyzed satellite data and ground-based telescope data, and developed computer programs and simulations, just to name a few of the things they've been doing this summer. Let's see if I can skip ahead. There was our students there. We recruit for the REU program from all over the country. This year's students were selected from over 100 applicants to the SETI Institute program, and they come from Massachusetts, New York, Florida, Kentucky, Montana, and right here in California. We also partner with the COMPARE program, which is a program designed to support students from a network of California universities and community colleges, and it's run by Alex Rudolph at Cal Poly Pomona. So you can see they're from all over. We've even got some. We need to go more heavily in the Midwest next time, I guess. In addition to their specific research projects, which they're going to talk about, one of the goals of the program is to expose the students to as wide a variety of research areas as possible. And to that end, they've been attending the weekly colloquium series here and generally getting a chance to have lunch with the speakers afterwards. They took a week-long field trip to Lassen National Park and Hat Creek to study geology and to make observations with the Allen Telescope Array. They've had a few personalized tours at NASA Ames, spanning a technology range from 1940s wind tunnels to one of the world's fastest supercomputers. And they got a nighttime tour at Lick Observatory and even got to observe through the 36-inch Great Refractor, which was commissioned in 1888. So I'll wrap up. I'd like to thank Jean Shar, who's been running this program for a while, Bill Diamond, who's been supporting the program, Edna DeVore and Alex Rudolph, and all of our mentors, many of whom are here, along with the SETI Institute staff for supporting this program. And I'd like to turn it over to our first student, Sean.
Hi, so my name is Sean Corrigan. In a week I will be a junior at Colgate University, and this summer I worked with Dr. Ginny Gulick on studying Mars gullies in Hale crater. So a lot of people mean different things when they talk about gullies. So I'm talking about this specific type of gully known as an ACA, which stands for alcove, channel, apron. So it's defined by an alcove at the top, a depositional apron at the bottom, and a channel in between. And more specifically, I studied these in Hale crater, which on this global map of Mars is right there with that arrow pointing to it. More specifically, 2 gullies within Hale crater are the ones that I focused on. And down here is a visualization of what it looks like just to get a feel of the landscape. So I'll start with my methods. My methods here are to measure the volume of the gully and its depositional apron. We do this because this kind of gives clue to how much volatiles were involved in the process, what the formation mechanism was, and if it was water, how much water was involved. So this method here is called the transect method. I just draw profiles, elevation profiles across perpendicularly to the gully, and it gives me something like this. So I just define two bank stations on either side, and I'll plug that into a computer program, and then that will output a volume for the gully. And I do the same thing for the apron there, and that looking at the differences between the two can tell me how much material was removed and how much is still there. This is kind of the same concept, but just a different method using ArcGIS. So another thing I did here was I looked at all the gullies in Hale crater. So that right there is a map of where all of those are. Looking at this, I could calculate some interesting characteristics of these gullies and figure out some more about them. So the results. The most interesting result I found was from the map of all the gullies in Hale crater. This rose diagram here is just a diagram that shows which way the gullies are facing, what the angle of the slopes is. Not the angle, but the direction the slopes are facing. And you can see that most of them are facing toward the south and a little bit to the west. And this makes sense because Hale craters in the southern hemisphere, southern facing slopes are going to be shaded most of the time. And having more shadowed terrain makes it easier for water to exist there. It's less likely to sublimate away. So that makes sense. Another thing we did was look at the volumes of the gullies, look at the volumes of the areas removed, and look at the volumes of the aprons and compare them. So up here we have the volumes of gullies, and down here we have the volumes of aprons. And the gully volumes are all much bigger than the volumes of the aprons, which means you can kind of tell how much water was involved in the formation process if it was water. And the differences between those are a good measure of how much was involved. And with that, that's everything. Thank you.
Hello, I am Patrick Carlson, a student at UC Berkeley where I study mechanical engineering. And my mentor for the summer was Alfonso Davila. And my project was to model deliquescence-driven microclimates in the Atacama. And so as a little background to this, the current paradigm for all searches for life on Mars is follow the water, look at lakes, send all our rovers to lakes to look for extinct life. But when we look at kind of our sample size of one for life of Earth, every domain of life that we know has both terrestrial and aquatic counterparts. And so the theory kind of behind this is that if life did evolve on Mars in an aquatic habitat, it would be able to, as on Earth, rapidly colonize land. And then in that case, life would then be independent of the existence of large bodies of water, as it would be atmospherically driven in terms of how it would live. And then it would adapt to dry environments in the same way as Earth microorganisms adapt. And in this case, particularly looking as when they colonize salt nodules and are able to absorb moisture from the atmosphere through a process called deliquescence, shown in the top set of slides, in which salt at a certain relative humidity, 75% for NaCl, will absorb moisture from the water, absorb water from the atmosphere, and then that water is able to sustain the microorganism living there. And so my project was to model this event. And so we have data from the Atacama that was collected by putting sensors in a Tupperware full of about a tenth of a meter by tenth of a meter by tenth of a meter with 3 sensors in it, one at the top, middle, and bottom. You can see on the left, with the black being the external relative humidity, the red being the top sensor, green being the middle sensor, blue being the bottom sensor, and how they reacted to this deliquescence event. And then on the right is my model of that I built to kind of try to recreate this scenario. And so it does a fairly good job. And you can see it's got some issues. It's a little sharper than reality. Dips come off quicker. So a continuation of this will be to attempt to apply this to different salts, as well as make it more accurately reflect the physics going on. So that I'm done.
Sorry. All right, can everyone hear me? All right, cool. So, good afternoon, everyone. My name is Brian Lopez, and this summer I had the opportunity to work with Matt Tiscareno on a project entitled Testing Machine Learning Algorithms to Find Propellers in Saturn's Rings. So first, let me just give a brief introduction as to what are propellers. These propellers are local disturbances that are created by relatively small moons that are embedded within the rings of Saturn. These propellers can vary in size depending on the size of their moon that is causing these disturbances. For example, a moon with a diameter of around 100 meters can create a disturbance that is as large as several kilometers. On the other hand, larger moons with diameters around around a kilometer can create a disturbance as large as several thousand kilometers. But take in mind the account that Saturn's rings extend to about 300,000 kilometers. Even these giant propellers are very hard to find by eye. We study propellers to understand and to gain a better understanding on how objects move within a disk relative to the body that they are orbiting. These propellers are important because by understanding how their orbits change over time, as we see with these giant propellers, we can understand, explain, and hopefully apply what we learn to newly formed solar systems. So here you can see the disturbance right there, which gives them that characteristic shape and their name. So how is this related to my project? Well, my mentor and his colleagues are a part of a challenge that was issued to the public to see if there was anyone that could come up with a way to use machine learning techniques to try and train a computer to find these propellers in the images from Cassini. My contribution to this program was to run and test the first and second place programs on around 30,000 images and see how well the program found these propellers. In addition, I also analyzed the output of the first and second place program and compared them with what my mentor found previously via the human eye. One of the goals of the challenge was to have a program place an importance score on the propellers that they found. If the program was doing its job correctly, it would place a high importance score on real propellers and a low importance score on non-propeller objects. The idea or the interest in going for this importance score was to weed out the many false positives that one may see when they're looking at the images, such as this right here. So with the propeller, you have more of an oval shape, which is what the computer was training to look for. And as it gets this, it'll mark it and give that a low importance score. In conclusion, the jury is still out as to whether or not this program is doing its job correctly, and more analysis will be needed to give a real answer as to if this program is doing exactly what we want. Thank you.
So, hello, my name is Nicholas Jung of the University of Louisville, Kentucky, and I'm going to be talking to you today about Boulder mapping of asteroid 1992 UI4. My mentor for this project was Dr. Michael Busch. So I'd like to give a brief background on UI4. So what exactly is it? It's a near-Earth asteroid discovered by Carolyn Shoemaker on October 25th, 1992. In August 2005, UI4 actually had a very close approach to us, coming within 0.04 AU of the Earth. Now, to put this into perspective, this is about 16 times the distance from the Earth to the Moon, which on astronomical scales which is pretty close. On August 1st to the 10th of 2005, Arecibo Observatory and the Goldstone Solar System Radar actually performed delayed Doppler radar imaging on the object. They were able to obtain images with a resolution as fine as 7.5 meters per pixel, and what they found was a lumpy and modestly asymmetric object not unlike a meatball. So since then, many scientists have characterized UI4, some of which are its mean diameter of about 2 kilometers and its rotational period of about 12.9 hours. But it's been yet to be seen what can be said about the Boulder distribution. Now, at this point, you might be asking the question, why do we care about boulders? Well, to put it simply, understanding the Boulder distribution on any given asteroid is very important for future mission planning and understanding the history of the asteroid involved. So in this project, what counts as a boulder? Well, I want to take a side step to just say that for this, we only use the Arecibo images, as the Goldstone images didn't achieve a fine enough resolution to find any candidate boulders. So if you notice in this upper right image, you can see these relatively bright clumps of pixels moving rotationally along each frame. So if we notice this feature, we call it a boulder, and we map its location onto models that we created using shape software. So what we found was that there were about 18 boulder candidates indicated by the white orbs in the bottom right image. We found that their distribution in longitude actually corresponded to the longitudes viewed by Arecibo on multiple days, indicated by different color shadings. You might also notice that there aren't that many boulders on the edges of Arecibo's vision, indicated by the orange and pink shadings, but this is likely observing bias by us. So with the available data, we can't determine anything about the boulder distribution. More observations would be needed in order to map the rest of UI4, but unfortunately, UI4's next flyby won't be for the next several hundred years. So although we didn't find what we were looking for, it's a good start. Thank you very much.
Good afternoon. My name is Jasmine Garani from Stony Brook University, and this summer my mentors were Eric Neilson and Franck Marchis. And my project that I worked on was called the Snapshot A-Star Survey, or SASSI, which is a direct imaging survey of A-stars. Now you might ask, what is direct imaging? Direct imaging is just one of many techniques we have to detect exoplanets. It is different than some of the other techniques, such as transits, which is what the Kepler Space Telescope uses, because we actually are able to see the planet, which allows us to take spectra to determine mass and temperature, which allows us to constrain formation models for the planet and the star system it's in. This survey used one of the two Keck telescopes, which is shown in the image on the right. And just on the image on the left just shows an example of an exoplanet discovered by a different instrument that was imaged by the instrument we used. This survey was done by Eric Neilson, one of my mentors, in the years 2013 to 2014 over 4 nights, and included about 600 images per night and a total of 200 stars. And the main question for this survey is, are there any planets? So my job this summer was to implement a data reduction pipeline which would take the image on the left and turn it into the image on the right. The image on the left is just a raw image taken directly from the instrument, and the image on the right shows what happens when it goes through a data reduction pipeline. This pipeline includes things like bad pixel reduction, taking out the bad pixels, taking out instrumentation error, and then also subtracting the starlight so it's easier to see the fainter objects. I have circled several of the candidate companions, and you can see, especially if you look at maybe number 16, that it's much easier to see these candidates in the process image than it is in the raw image. And we can quantify this by finding the signal-to-noise ratio, which basically means that we have a point source and a background behind the point source. And we take the maximum brightness or pixel counts of the point source, and then also the standard deviation of the noise, and divide. So you divide the maximum by the standard deviation, and then you get the signal-to-noise ratio. And between the raw image and the process image, the signal-to-noise ratio improved by about 4.2, which means it's about 4 times easier to see the objects in the process image than it is in the raw image. So this is what I've done so far in the summer, and I'm going to continue working on it to try to get better images and then to identify candidates. Thank you.
Hello, everyone. My name is Miles Currie, and this fall I'll be a senior physics and astrophysics student at the Florida State University. And this summer I worked with Drs. Susan and Fergal Mullally on a new method for cleaning K2 data. So before I jump into my research, I wanted to briefly mention the Kepler mission. So what it is a telescope that was meant to detect exoplanets using the transit method. So when a planet passes in front of a star, it blocks some of its light, and it creates a dip in this light curve, as you can see here. So when some hardware failed on K2, we repurposed this mission, or we continued this mission with, we continued this mission with the K2 mission. And what's different about the K2 mission is that it doesn't have some of the hardware that Kepler had. So it's subject to the sun's radiation pressure. And the sun's radiation pressure kind of makes it roll a little bit like this. So to correct for that, it has to fire its thrusters every now and then. And that creates this distinctive rolling features in these light curves that you can see here. This is a K2 light curve, and zoomed in, you can see these rolling features. So my project this summer was to take out these rolling features using principal component analysis at a pixel level. So it can be explained through these images. So over here we have a sinusoidal curve, and this can represent a single pixels time series light curve. And so what we do is we find commonalities in the pixels in the aperture, in a K2 aperture, and we take out we decompose these into its principal signals. So we take the principal signals that have these rolling features that we don't want, and we literally subtract them from the original light curve. So applying this to some K2 light curves, real data, in the blue you're seeing these are two stars light curves taken by K2. When we applied principal component analysis to this, we took out the signals that have the rolling noise that we don't want, and we subtracted them off, and we got these green curves down here. Now you can see that there's much less noise compared to this area right here, and the transits are preserved, which we can use for later analysis. And I'm currently running an analysis on about 4,000 stars with this. It's not done yet, but that's what I'm going to investigate next. So thank you.
All right, hi everybody. My name is Raina Rampali, and I'll be a junior astrophysics major at Wellesley College this fall. This summer, I worked with my mentor, Joseph Catanzarite, on calculating the occurrence rate of hot Jupiters. And what this essentially means is you can actually figure out the number of planets in a certain phase space by using massive amounts of Kepler data. And the phase space of interest for me was the hot Jupiter phase space. So those planets that are Jupiter size and have very short orbital periods around their parent stars. And these planets are really interesting for two reasons. The first being that although we can detect them quite easily from ground-based detection schemes, they're actually quite rare if we compare them to smaller sized planets like Earth's, for example. And secondly, we actually don't know a whole lot about how these planets are formed. So finding a very accurate number for the occurrence rate could lend us some insight into how these planets are formed and just the planets themselves. So one way of going about doing this and finding more accurate number is by introducing this idea of probability or reliability. So a lot of objects like eclipsing binaries actually have signals that mimic those of hot Jupiters. So the Kepler team has published this list of probabilities associated with each hot Jupiter candidate on the basis or the likelihood that these candidates might actually be false positives. So one thing I did over the summer was actually first define what a hot Jupiter was. So hot Jupiter has a radius from Saturn size to 2 times Jupiter size, and a period ranging from 1 to 10 days and 10 to 100 days. And I went through and calculated the occurrence rate in each bin, including the reliability and not including it, and seeing if there was a significant difference between the two. So we see here there actually is a decrease in the occurrence rate once you include reliability, and this is actually a percent decrease of about 10 to 12%, so it's pretty significant. And if we consider this on a holistic level, so looking at a period range from 1 to 100 days, there's actually a 35% decrease in the occurrence rate. So the occurrence rate falls from 2.7 to 2%. And this is really statistically significant, as I mentioned, because you're looking at a difference that's about at least 1 sigma. And so my plan is to incorporate these reliabilities into looking at the hot Jupiter candidates' parent stellar metallicities and seeing if there's any relationships there that could help tell us anything about the formation of these planets. And I'd just like to acknowledge the following people, institutions, and paper I used during the summer. Thank you for your time.
Hello, everyone. My name is John Santiago. I'm a physics major at Cal Poly Pomona, And this summer, I worked with Peter Tenenbaum and Douglas Caldwell on TESS. So TESS is the Transiting Exoplanet Survey Satellite, and it is expected to be launched at the end of next year. My project has to revolve around this image right here. So early pictures taken by the TESS detectors, we see that as the wavelength of light increases, we start to see bright bands appear in the images. And at first, this seems like a problem. So my project was to determine how much these bands affect the images and, more importantly, affect finding transiting exoplanets. So the method I used was I applied a flat field to basically some of the test code called Lilith. This is my flat field right here. It has a ton of bright bands. The more, the better, because I want to maximize the amount of targets that fall on the bright bands in order to study their effects. So I applied this to a field of 1,300 targets, and I wanted to see I want to compare the photometry and the centroids of the targets to basically a field without this flat field. So I have like a good comparison, and then I have a comparison with this. So what I ended with was this graph. So this is the photometric results of my project. On the x-axis, I have the test magnitude. So these are ranging from about 7.5 to 12.5. And then on the y-axis, I have the relative noise. The red line is the photon statistics of what the TESS spacecraft is receiving. And most importantly, each of these blue dots represents one of the 1,300 targets that we looked at. And we wanted to see how the noise of each of the targets compared to this red line. Basically, what we're looking for is if any of these targets we saw a large increase above this red line, it would have been a bad thing and would have meant that these straps had a large impact on the images. However, thankfully, we found that none of them go on top of this. So photometrically concerning, these bright straps don't have a huge effect. And that was with the flat field I showed in the beginning, how it had 100 of the bands. So the next step of my project is to do the same thing with centroiding, and hopefully that'll be done by the end of this week. Thank you.
Okay. Hello, my name is Leah Weston. I go to CSU Sacramento. My mentor, Dr. Jerry Harp, and I have been searching for the WOW signal using the Allen Telescope Array. For those who don't know what the WOW signal is, it was a strong narrowband radio signal that was discovered by Ohio State University in 1977 using the Big Ear radio telescope. So the signal appeared to come from the constellation Sagittarius, and it also appeared to be extraterrestrial in origin. The astronomer who was reviewing the data at the time was so impressed by the signal that he wrote WOW next to it, hence the name. There have been many searches for the signal before, but unfortunately has not been found since. So that's where we come in. And the ATA has spent roughly 10 hours out of a target of 100 hours observing the source of the WOW. So this long of a search has not been done before. The raw data that comes in from the ATA is processed in 3 main steps. The first thing that must be done is to take out all the bad data. The data could be bad either from radio frequency interference, or it could be just instrumental errors. To determine the bad data from the good, a calibrator is observed. So the calibrator is a known point source. Since we know what the calibrator should look like, we can take out all the data that does not match the expected values. We can then take out this same set of flagged data from our WOW observations. After this, we have to focus the calibrator. When we get it to look like it should, we apply the same parameters to the target source. And finally, we create images of the calibrator and the source, which look like this. So the top images that you see are of the quasar 3C380, which was used as the calibrator for the WOW observations. These images are really important because they show that we have successfully gotten rid of almost all of our radio frequency interference or other bad data. The pictures on the bottom, however, are the interesting ones. So let me rewind a bit here and tell you that the original WOW signal could have come from two areas of the sky, so about here and about here. Unfortunately, there was some ambiguity, a small ambiguity in the original data. So, but our picture actually has both of these areas in it, which in this type of observation hasn't been done before. So there is some noise here, which shows up in the darker blue, shows up as darker blue in the WOW source images. But as you might be able to make out in these pictures, there are a few radio sources toward the bottom right. We know these are real because they show up as point sources in our images. Unfortunately, these features are natural and they are found in the NRAO VLA Sky Survey. We still have about 90 hours of observing to do, however, so the search continues. Thank you.
Good afternoon, everyone. My name is Morgan Henderson. I'm a physics student at the University of Montana, and under the mentorship of Dr. Uma Gordy, I have spent the summer investigating the recent observations of carbon monoxide emissions coming from debris disks around 30 to 40 million year old Type A stars. Specifically, I've been working with the debris disks shown here in lovely spatial resolution, courtesy of the ALMA array down in Chile. Now, to begin my talk, I would like to first discuss the impetus of my research. Why does the detection of carbon monoxide in these disks prompt further investigation? Quite simply because we don't expect gas to exist within these disks. As you can see in the figure to the left here, the frequency of disks around stars in a population decreases greatly with the age of that population. Basically, the material in these disks is used up over time in the formation of rocky and gaseous bodies, or is simply blown out of the disks entirely by stellar radiation. This not only causes a lack of disks around aging young stars, but it also means that in disks which persist around stars greater than 10 million years of age, there is very small amounts of gas, and the disks are primarily composed of diffuse dust populations. As you can see in the figure to the right, even the dust in these disks is limited in its mass, and in fact, none of these stars older than 10 million years represented in this plot have disk masses greater than a single solar mass. So returning to the subject of this talk, where are these emissions from the disks around A stars coming from? Well, the earliest papers on this subject conclude that the gas in these disks are likely left over from stellar formation, and that what we're witnessing is a new stage in protoplanetary disk evolution. However, the research which I have been doing focuses on a model which argues that the gas in these disks is actually likely produced via collisions and is then excited by dynamic events in the disks. By modeling the three disks which I showed you at the beginning of this talk, I was able to constrain the values of some physical parameters of these disks given both of the genesis situations. By modeling the line profiles of these disks, as shown in this figure, I was able to determine the temperatures and number densities of gas necessary to produce the observed emissions. And by combining these parameters with physical and mathematical models, such as the black body analysis shown in this figure, I was able to determine estimates for the mass in these disks, as well as the production rate and lifetime of carbon monoxide in these disks. Now, these procedures revealed that the masses required for the original gas situations would actually exceed a single Earth mass, contrary to the figure which was shown to you on the previous slide. These and other preliminary results actually suggest that perhaps the collisional production of this gas in these disks is actually a more feasible explanation of the observations that we see than was previously thought, and that perhaps original populations of gas within the disks is actually a less feasible explanation for these observations than was previously thought. And with that, I have just about exhausted my time, so thank you very much.
Good afternoon. My name is Pierre Casco. I'm a student at the University of Miami, a geology major, and my mentor for this summer has been Friedman Freund. The title of my talk is Infrared Reflection from Rock Surfaces When Stresses Are Applied. Now, this is important to be able to maybe possibly forecast earthquake by recognizing different precursors caused by stress. One thing I learned about earthquake and the force and energy that they give out is a magnitude 9 earthquake like the one that occurred off the coast of Japan a few years ago released energy equivalent to about 2 million Hiroshima-class atomic bombs. So that's a lot of energy. If we could help forecast that and give people warning, maybe there's a better chance of survival. So first, what I'll speak about is the pyroxy defects. These pyroxy defects are found in all rocks at the Earth's surface and beneath the Earth's surface. What it is 2 oxygen anions linked together with a missing cation. When these bonds are usually very hard, but when they are stressed, they could be broken. So what happens is that the link is broken and a neighboring oxygen anion shares an electron, and this causes a charge carrier known as a positive hole. These positive holes propagate outwards from the stressed portion to the unstressed portion through quantum mechanical effect. So what happens is that every oxygen anion, instead of sharing one electron, they all share a piece of their electron density. So it essentially is every oxygen anion around the hole is at approximately negative 1.99 charge. I used two ways to stress the rock. I used a ultrasound transducers 40 kilohertz with a 100 watt generator to stress, and I also used a 70-ton hydraulic press inside the engineering lab in our building. This is the spectrum that I got from the ultrasound transducer. If you notice that it's pretty constant here, this is just atmospheric noise. The blue is the no ultrasound, and once the ultrasound was turned on, then these molecules here in the 1900 to 2000 range, which is CO double bonds, gets excited, as well as small over here in the 1600 range, which is H2O molecules being excited by the vibration. So with this, maybe we can come up with, with further research, we can maybe possibly come up with precursors that we could use to forecast earthquakes. So, thank you.
Thank you, all the students. We will have time for questions now. If anyone has questions, the students can come up, or I will pass around the mic. Yeah, students should come up, and that way you can answer your questions. We'll start with Jerry.
Thanks, Ted. Morgan, let's see, I can't find you now. There he is. In the images that you showed, I don't know if the field of view is a microarcsecond or if it's a degree. And so it'd be nice if there were something on a scale. So that
the scale exists as far as arc seconds. I'm failing to remember right now, but I can tell you that in general they are all in AU around 150 AU disks. One of them is 65 to 150 AU. One of them is 35 to 150 AU, and one of them is around 1 to 135 AU. I could have had that. I'm sorry.
This is for Leah. The picture you showed of the two fields for the WOW image, there were point sources that you said were real because they're known sources. You referred to the diffuse light, I guess medium blue, as noise, but that was also consistent between the two images, not completely in all detail, but more or less. So isn't that either some background emission or something?
Well, so those
Other
had
than
like,
the-
if you notice, they kind of had like a wavy pattern to them, which
Yes.
means they're probably RFI. So it's probably just some RFI that's kind of constant over, it was August 5th and August 7th, so not too long ago. So it's probably some constant RFI that we're getting from somewhere near the ATA.
I see. Thanks.
Hi, I'm Joe Catanzarite from SETI. I have a question for Miles. So how did you, in your principal component analysis, how do you remove or separate the transit signal from the bad stuff, from the rolling motion signal?
That's a good question. So we hypothesized that the most influential principal components correspond to this rolling motion, and I have an algorithm that kind of chooses the first few. It's not. I don't have a great way of doing it yet, but currently I'm finding about 1 in 4 transits in my data. I ran it on about 100, and I was finding like 25 out of the 100 transits. So.
My question is for Leah. You talked about finding some light sources, and after you did the data processing, the signal-noise ratio had increased by a factor of 4. The signal-noise ratio was 4 times higher.
Oh.
Pardon?
That was
Isn't
for
that
me.
Wasn't it? I'm sorry, Jasmine. It was Jasmine. Thank you. Yes.
I'm
In
sorry.
any case, signal-noise ratio was a factor of 4 larger. With SNR4, the chances of having a random event now drop not by a factor of 4. The chance of you identifying a random event dropped by a factor of 1,000. Isn't that the case? That was a dramatic improvement in your ability to recognize a real object from a statistical fluctuation.
So I think one of the reasons why it was probably a big difference is because I was looking, when I did the signal to noise, is I was looking at objects that were very, very close to the star, which means that in the raw image there was a lot of starlight, and then we took most of that starlight out, so that's why we got the big increase.
But I think it's a very big increase. You suggested it was only a factor of 4. Statistically, it would be much more prominent than a factor of 4, maybe a factor of 100 or 1,000.
I mean, that's what I got when I was doing the analysis. I was going to do it again because I learned a new technique to do it, but I just hadn't had time to do it before this. So we'll see what happens when I fix that. Just ran out of time.
Hi, this question is for Nicholas. Given that 1992 UI4 is not going to be around anytime soon to look at, did you learn anything from the techniques that you used that you could apply to the study of boulders on other near-Earth asteroids?
Well, during the process of modeling it, we also found its pole direction. So we found that it was a retrograde rotator. It can be applied to other near-Earth asteroids, I believe. Sorry.
Do you have any plans to do anything with that?
I'd like to continue if Michael would have me over the semester, but I don't know. I think I've been a hassle.
Sean Corrigan about the Gullies. Stepping back a little bit, for someone who doesn't know all that much, the deposition and so on, is that a smoking gun for water flow along the gully? Is that the standard idea of what's going on there?
It is a pretty popular idea right now. It does seem like a fair bit of evidence, but there are some other theories proposed that say that it could be dry processes, but it really doesn't look like that's what it could be for that. And the difference between the volume removed from the gully and the volume deposited in the apron is a good measure of what might have been there before but left from the apron.
I see. And you studied the sort of directionality of the gullies, but can you learn something about the distribution? I mean, it looked like they were within a crater typically. Can you learn something from how the gullies are distributed within the crater?
Yeah, so they were mostly on the rim and in the central peak of the crater, so they have to be on a certain slope angle in order to form. So if the slope's too low, then the gully probably isn't going to have enough downward energy to form anything there. Also, the characteristics of the slopes are important. So if they're facing south, then they're more shadowed, and if they're more steep, then more of the slope will be shadowed, so the water can stay there and stay stable for longer.
Okay, so this my question is for Pierre Castro, and in your talk you show a peak intensity at the infrared spectrum, and you said that is to detecting the earthquake. And my question is that do you have any? So my understanding is that if you have earthquake, so you have a peak intensity like that you show, but do you have any other sources? As this infrared spectrum that also have other peak intensity?
Yeah, there's along with the reflectance and also emission, there's also a change in the air ionization. Once these positive holes gather near the top of the unstressed portion and they recombine, they release IR photons, and also they release they release ions into the air, which go up into the ionosphere. And they could also cause magnetic, ultra low frequency magnetic storms as well. So yeah, there's other ways other than that.
This one's for Miles. So couldn't you have used the telemetered rates and attitude of the Kepler spacecraft to adjust the data instead of the principal component method?
This is just a different method that we're trying out. It's a novel method. Fergal has something.
There's lots of us in this room that can answer that, I think. I mean, the problem is that they generally either are low resolution or at different time sampling, and the stars themselves actually tend to give you a better, higher fidelity signal to find out what's going on. So you look for common mode things among the stars. We have. People, that was one of the standards. We're trying to improve on that.
That's a question for Pierre Casco. How much lead time warning would we get if this method works for predicting earthquakes?
I've seen about a week lead time.
So for Brian, so you were looking at these 30,000 A-ring images looking for propellers using these two different algorithms, right?
Yeah.
When you were comparing the results of these two algorithms on all of these images, since we don't actually know where the propellers are in those images, how were you figuring out which algorithm was actually doing a better job?
Well, actually, the outputs of the algorithms do give a coordinate on where the propeller was found in the image. Also, my mentor has a pretty extensive list of all the propellers that he found by eye, which also have X and Y coordinates. So that's kind of, I guess, a ballpark.
So you went back and looked at them by hand, basically?
Well, my mentor did, so I was kind of just going off of his list.
Ah, okay.
Yeah.
So do you know what the results were? How did it do?
So far, it looks like the program is catching all or most of what he found, but I think for each image, the program looks at 10,000 candidates max. So I know it's some really large number. So, but as far as I could see, it seemed to compare with what my mentor found.
This is a question to, to Morgan and also for Pierre, because you made a case that the CO in these disks is constantly replenished, otherwise it would diffuse away and get lost. Now in Pierre's data, we have shown in other experiments that when we stress rocks, which he did in case of ultrasound, there's actually a emission of CO from the surface. And this emission of water, both water and CO, it actually occurs in an excited state, in vibrational excited state. So there is a source of gases being emitted from solid material when they are subjected to mechanical stress. It may also work with hard UV, and that would be complementary to what you found.
Yes, absolutely. And in fact, it's been proposed that a lot of the carbon monoxide in these cometary bodies, in these disks, could actually be trapped within crystalline structures of water ice. And yeah, these dynamic collisions can cause greater release of carbon monoxide than is traditionally thought of, because currently most of the models that have been run on these events assume that the carbon monoxide and the water ice and the rocky silicate material all exists in the same relative abundances that they would primordially in the interstellar medium. And yeah, you're absolutely correct. Because of the co-location of water and carbon monoxide, and because water ice is torn apart very easily, even at just sound speeds and lower, even at like 70 Kelvin. Yeah, there are a lot of reasons to think that dynamically there should be no problem to release carbon monoxide from these cometary bodies.
Yeah. Thank you. May I just also make a comment to the infrared anomalies that are observed? Essentially, every major earthquake that was available for analysis from satellite, that means clear sky, showed a anomalous infrared emission equivalent to about 10 to sometimes 15 degrees on the Planck curve a week or so before earthquakes. And that seems to be spectroscopically distinct from the Planck curve.
Another question over here.
My question is for Raina. You were looking at the frequency of hot Jupiters, and the answers you've got were about 0.5% and 1.5%, with a total of about 2%. How does that agree with what's in the literature?
Right, so I actually am only certain of the 1 to 10 day period, and Natalie Batala got an occurrence rate of 0.5%, so that's an agreement. But with the probabilities incorporated, that percentage falls a little bit.
I'm sorry, did what?
It falls a little bit once those probabilities are incorporated by about 10%.
But your value is that's already in the literature, is that right?
Right, correct.
Thank you.
Any more questions? Last chance. Let's thank our students one more time. And if you're interested in hearing more about these topics and are over at the SETI Institute, they're going to be giving a longer version of these talks, about a 15-minute version of these talks over the next 3 mornings, starting from 10 to 11. There's about 4 students per day, Wednesday, Thursday, Friday. So if you're at SETI Institute, it'll be in the Bloomberg room. And thank you again. Oh, awesome job, guys.